Hello, my name is Kelly Zoe, and this is Lab 4, Circuits and Capacitors. So the objective of this lab was to use an online simulation to observe how circuits work in series and in parallel, to find the values of the current and potential difference of that circuit, and to observe the behavior of resistors and capacitors. So some of the physics concepts used in this lab were the loop rule, the energy conservation, more so in current conservation, and resistance equation. The overall result I got at the end of the lab was that the computed RC value was 6.58 seconds. So the predicted value of the current 1 and current 2 is 0.0204 amps, which is found by I equals V over R, which is 3 volts over 147 ohms. The ammeter value for I1 and I2 from the simulation reads as 0.02 amps, as you can see in the first picture. And when the ammeter is backwards, the value of the current is the same, which is also 0.02 amps. The voltmeter, when in substitute of one of the ammeters, reads 3 volts, and the ammeter reads 0 because the circuit isn't closed. So here, the first picture shows the potential differences across different points of the circuit. So as you can see, the potential difference across the battery is negative 3 volts. The potential difference across the 47 ohm resistor is 0.959 volts, and the potential difference across the 100 ohm resistor is 2.041 volts. And the sum of all the individual potential differences is 0 volts. The second picture below shows a graph of the potential difference over the position of the circuit. So as you can see, from C to D, it's decreasing down, and from D to E, it stays the same because there is a potential difference of 0 voltage, and then there's a decrease again from E to F, and then from F on, because it's all wires and the ammeter, it is at 0 volts. So the ammeter doesn't read a change when the voltmeter is added because the voltmeter has high resistance and therefore does not redirect the current. With the ammeter in parallel, as you can see in the picture below, the current reads 0.06 amps. The current increased because the ammeter has low resistance, and so the current just flew through. Here's how you find the resistance of different circuit elements. So you're using the formula the delta V over I. So for the 47 ohm resistor, the resistance was 47.95 ohms. For the 100 ohm resistor, it was 102.05 ohms. And then for the wired ammeter, it was both 0 ohms because there was a 0 potential difference. So here is the diagram for the RC circuit portion of this lab. Here are my observations. The light in the bulb is bright originally, but as the capacitor is charged, the brightness dims until there is no more light. When the bulb is connected to the onto the charge capacitor, it is brighter for longer, but it dims as the capacitor discharges. And when the battery was attached, the current slowed down as the capacitor was being charged until the current stopped because the capacitor was fully charged. And when the battery was removed, the current slowed down until the capacitor was completely discharged. So here are the different times it took for the capacitors to charge and discharge at different resistance. So at a resistance of 10 ohms, it took 5.49 seconds to charge and 6.29 seconds to discharge. And for 20 ohm resistance, it took 10.12 seconds to charge and 14.83 seconds to discharge, which is roughly twice as long as it took for the 10 ohm resistor. So here I was trying to calculate the RC value. So I took the voltmeter readings at each second and took the natural log of V over V naught and plotted that natural log on this chart. And to find the RC, which is the time constant of the circuit, what you do is the slope is equal to -1 over RC. So taking that, which was negative 0.1519, taking that value as the slope, I calculated the RC value to be 6.58 seconds. And the computed RC value above does agree with the RC value of the CCK, which is simulation, because that is 30 times 0.2, which gives you 6 seconds. So in the conclusion, what if I were to do this lab in real life and using an actual ammeter instead of an ideal simulated ammeter? So an actual ammeter would have more resistance, and therefore the value of the current will be lower than found in this simulation. And what if I were to do the lab in real life and use a real battery to charge a real capacitor with no resistor in the circuit? How quickly would my ideal model predict a capacitor to reach full charge? I said that the ideal model does not take into account resistance within the battery and the wires, so the capacitor is charging instantly. However, in real life, we would expect this to take longer.